So in the previous question, the parachute is connected to the rock with a single string. When is the string under the greatest tension? And why do you know? Well, so let's see. We have something like this. There's a parachute and there's a string on the rock. And I know the force of gravity is pulling down. So already I want to know when this tension is the greatest. And so I'm looking at a mass and there's possible accelerations and forces. I'm going to try a dynamics lens because we're dealing with forces and acceleration. And so immediately I know I'm going to have to solve the vector sum of the forces equals mass times acceleration. We don't waste any time. So let's look at the forces and the acceleration. We have tension pulling up on this guy, and we have the force of gravity pulling down. Now, if the tension is greater than gravity, then the acceleration will be upward. If the tension is less, then the acceleration will be downward. And so I'm going to want the time when the tension is the greatest, which is going to be when the acceleration is the greatest upward. And that's right when the parachute opens. That parachute opens and the tension is really high, much greater than gravity. And the velocity slows from 10 meters per second to 4 meters per second. So like here, we're all falling together and the parachute goes up. So why does this happen? Well, here we're all falling together under the force of gravity, and probably we're not accelerating anymore because now the force of gravity is equal to the air friction and we're all falling at constant terminal velocity. Then this guy opens his parachute and the tension from the parachute cable is way greater than the force of gravity. And this unbalanced force causes him to accelerate upward in a big way. So I'm going to call this the positive direction. And I'm going to label acceleration is in this direction at 20 meters per second squared. And if I wanted to, I could write it's a 2 kilogram rock and the acceleration is 20 meters per second squared. So this is 40 newtons upwards because the acceleration is upwards. So would I write that as my answer? And the answer is no. Right? This is the total force upward to cause its acceleration upward to cause it to slow down. Tension is only one of the two forces. So what's that look like? If we added the force of gravity to the tension, this is what it would look like in equilibrium, where the tension is equal to the force of gravity and acceleration is 0. But we have a situation where the tension is much greater, and therefore the total force, the sum of the force of gravity and the tension, is equal to ma. And I can write the vector sum of the forces if I want. I like it because the vector sum of the forces is in the same direction as the acceleration. And so now I don't really need to write the equation out. I can see that this is 20 newtons, mg. Force of gravity equals mg is equal to 2 kilograms times 10 meters per second squared is equal to 20 newtons, and it's downward. So I could put down this is 20 newtons. And then this is 40 newtons. So I know this guy has to be 60 newtons. 60 newtons is 40 newtons greater than 20 newtons. But if I were to explicitly solve this problem, I would say, oh yeah, the vector sum of the forces, you have the force of gravity, and you have the tension, and that equals to mass times acceleration. And now I've got 20 newtons plus the tension, which I want to know, is equal to 40 newtons. Now, very importantly, we recognize this is the positive direction. I've chosen it. And so this is a negative number, and this is a positive number. And we could put vector components on them in the y direction, if we want. And then we have tension is equal to 60 newtons in the y direction. I love it.